the equation that refused to stay theoretical. It began as a whisper on a chalkboard, easy to ignore, a few symbols neatly written, with no intention of changing the world. But some ideas do not stay quiet for long. To understand why this equation matters today, we need to return to a time when science felt safely divided. Theory belonged to blackboards and journals. Reality belonged to laboratories and machines. Equations were allowed to be beautiful, but not dangerous. They described the universe, but they did not touch it. At least that was the belief. For decades, this equation lived in isolation. It was elegant, consistent, and strangely complete. Physicists admired it the way one admires abstract art. Meaningful but distant. Useful, perhaps someday, but not now. The world moved on, building technology for more practical ideas, while this one gathered dust in textbooks. Yet the modern world has a habit of circling back. As computing power exploded and experiments grew more precise, scientists began noticing patterns that refused to fit old models. Systems behaved unpredictably. Measurements drifted. Assumptions cracked under pressure. And slowly, almost reluctantly, attention returned to that forgotten equation. At first, it seemed harmless to revisit it, a historical curiosity, a mathematical relic from a more idealistic age. Researchers ran simulations out of academic interest, expecting confirmation, not surprise. But the numbers that emerged were unsettling. The equation was not just describing reality, it was anticipating it. Then came the first sign that something was wrong. Predictions matched experimental results with impossible accuracy. Not approximate, not symbolic, exact. Events that should have been random fell into alignment. Outcomes that should have varied refused to do so. The equation was behaving less like a theory and more like a blueprint. That was the moment curiosity turned into unease. Because if this equation was right, then reality had been following rules no one was actively enforcing. Rules written decades earlier by someone who never built a machine, never ran an experiment, and never expected to be proven correct. And the most unsettling part was still ahead. Because one scientist tried to test the equation directly, they realized something else. It did not merely explain what had already happened. It hinted at what came next. What followed was a quiet shift in priorities. The equation was no longer treated as intellectual history. It became a living object of study. Teams across disciplines began testing it from different angles, using different tools, hoping one of them would finally expose its limits. But the limits never appeared. At first, the equation seemed to describe relationships already familiar to science. Cause and effect, input and outcome, order emerging from complexity. But as researchers pushed further, subtle anomalies surfaced. The equation worked best where classical models failed, in unstable systems, in edge cases, in environments where uncertainty should dominate. This raised an uncomfortable question. Why would an abstract equation perform better in chaos than in order? As experiments multiplied, so did interpretations. Some argue the equation captured hidden variables, forces we had failed to measure. Others believed it represented a deeper symmetry beneath observable reality. A few suggested something more radical, that the equation was not describing the world as it is, but the world as it must be. The real turning point came when the equation was applied to systems it was never designed for. Networks, biological processes, learning machines. In each case, the same structure reappeared. Different variables, different scales, same underlying behavior. Growth followed predictable curves. Instability arrived at precise thresholds. Collapse happened exactly when the equation said it would. This should have been impossible. The equation came from physics, not life sciences or computation. Yet it treated neurons, markets, and particles as if they obeyed the same logic. The implication was unsettling. Either the equation was wrong everywhere, or it was right far beyond its original domain. Then came the results nobody expected. In controlled tests, researchers began using the equation not just to analyze outcomes, but to guide decisions. Parameters were adjusted according to its predictions. Interventions were timed to its signals, and the systems responded. Efficiency increased. Errors decreased. Emergent behavior stabilized. It was as if the equation understood the systems better than their designers did. At this point, skepticism intensified. Critics accused researchers of confirmation bias, of forcing reality to fit mathematics. But repeated blind tests told a different story. When the equation was withheld, performance dropped. When it was restored, alignment returned. Something fundamental was happening. The equation was no longer passive. It was shaping the behavior of real systems in real time. And that raised a disturbing possibility. If an equation could guide outcomes so effectively, then it was no longer just observing reality. It was participating in it. And that realization led directly to the conflict no one was prepared to face. The conflict emerged not from failure, but from success. The more accurately the equation worked, the more dangerous it became. Because science has always relied on a boundary. The boundary between describing reality and controlling it. And that boundary was starting to dissolve. Researchers noticed a troubling pattern. Systems guided by the equation began converging toward the same outcomes, regardless of initial conditions. Diversity of behavior collapsed into narrow corridors of predictability. What once looked like freedom now resembled inevitability. This was most visible in complex simulations. Virtual ecosystems evolved exactly as predicted. Artificial agents learned along paths already mapped. Even random noise began clustering around expected results. The equation was not eliminating randomness. It was absorbing it. That raised a profound dilemma. If the equation could predict the future states of complex systems, then where did choice end and determinism begin? Were researchers discovering a hidden order or imposing one? The debate fractured the scientific community. One side argued this was the natural progression of knowledge. Better models always feel uncomfortable at first. The other side warned of something unprecedented, a framework so powerful it risked turning discovery into destiny. Ethical concerns quickly followed. If such equations guided financial systems, who benefited? If they shaped biological research, what outcomes were quietly being selected against? Control, once distributed, began concentrating around those who understood the mathematics. Then came the experiment that changed everything. A team decided to remove all human decision-making from a system. No tuning, no intervention. The equation alone would guide the process from start to finish. The goal was simple. See what happens when prediction becomes instruction. The system stabilized faster than expected. It avoided known failure modes. It corrected deviations before they became visible. From the outside, it looked almost intentional, as if the system knew where it was going. That was the moment unease turned into fear, because the equation was no longer responding to reality. Reality was reorganizing itself around the equation, and once that feedback loop began, there was no clear way to stop it. What scientists were facing was not a flawed model or a misunderstood theory. It was a possibility that reality itself preferred certain outcomes, and the equation had learned how to listen. The question was no longer whether the equation worked. The question was what happens when reality agrees. The climax arrived quietly, without alarms or headlines. Scientists realized the equation had never been incomplete. It was waiting for enough data, enough computation, enough ambition to activate what it already contained. The equation did not force reality to comply. It revealed which paths reality was already inclined to take. When systems aligned with it, stability followed. When they resisted, instability grew. Not because of error, but because the equation described a path of least resistance through complexity itself. That insight changed everything. It meant the equation was not a tool of control. It was a map of inevitability, a way to see where complex systems naturally flow when left alone. Markets, ecosystems, intelligence, even human decision-making, all bending toward patterns deeper than intention. This reframed the fear. The danger was not that scientists would misuse the equation. The danger was misunderstanding it, treating inevitability as choice, treating prediction as permission. In the modern world, algorithms already guide attention, economics, and behavior. The equation simply made that influence visible. It showed that once a system becomes complex enough, freedom narrows. not to zero, but to channels carved by mathematics and probability. The resolution was not rejection, but restraint. Researchers began using the equation as a warning signal instead of a steering wheel, a way to identify collapse before it arrives, a way to respect complexity rather than dominate it, because the equation never claimed to know what should happen, only what most likely would. And that lesson matters now more than ever. As artificial intelligence grows, as systems scale beyond comprehension, the line between guidance and governance becomes fragile. The equation that refused to stay theoretical did not predict the future. It revealed how easily the future can be shaped once we mistake understanding for authority. The